Today we will cover chapter 9, deflection of beams. So what we did before is we figured out, like if we apply some loading on beams, we figure out how to find the shear stresses and also normal stresses. And today what we want to do is, so we want to figure out how much the beams would deflect under transverse loading. And this is an example. So we have a cantilever beam and you apply a load at the end at point A, and what you know is due to this load you know that it will deflect. And what we learned before is in chapter 4 we learned that the curvature, which is equal to 1 over radius of curvature, which is rho, is equal to the moment divided by EI. And what you can also realize is when you cut different sections, you will realize that this moment is changing with x. So at different x values, you have different moment values. And since E and I are constant, so from here you can guess that the curvature is changing with x or with the moment. So for this particular question, so you can find the moment at anywhere is equal to minus p times x, okay? And x is given from here. So when you increase the x, your moment will increase. So from there I can get this curvature. So what you see is the curvature is varies linearly with x, okay? And if you look at the end, so if you look at this point, what you will see is since your x is equal to 0, so this term will be equal to 0, and from there your radius of curvature will be infinity. So which means that basically you will have kind of flat, and at point B you can get this value. So you can get a specific value for this radius of curvature, or you can get the value for curvature. So which means that at any point, as long as I know my moment, I can determine what's my curvature or radius of curvature. Okay? And in another example, so let's assume that we have a overhanging beam and we apply these two loads at B and D, and then since this is supported, we know that you will get the reactions at A and C, and you can find them by using our statics knowledge. And then after that we can draw our moment, bending moment diagram, okay? And if you do that, so this will be our moment diagram. And then what it means that at any point I can use this equation. I can use curvature is equal to mx over EI, okay? Right? And from here you can also realize that when your moment is equal to 0, my curvature will be equal to 0. So at point A, E and D, my curvature will be equal to 0 because my moments are also equal to 0. And also when you look at this beam, so you can kind of realize how it deforms, okay? So you expect that it will be concave up from A to C, and then actually A to E, and then it will be concave down from E to D, okay? So which means that when your moment is positive, so your beam will be concave upwards, and then when your moment is negative, so between E and D, it will be concave downwards, okay? So from this moment diagram, I can guess how my beam deforms, okay? And also what else we will find is since I have this equation, I know that my maximum curvature occurs when my moment is maximum. So at this point, okay, and this point, so those 2 points where I have maximum and minimum moments, I will have the maximum curvatures, okay? But still what I'm more interested in is I'm interested in how I can find this deflection, like how I can find how much a point in the beam goes downward or upward. So I need to find my elastic curve equation, okay? And for this we will use math, and I'm not going to go into details, but from math we can find that our curvature is equal to d square y divided by dx square. So y is the deformation, so y is the deflection in towards the y-axis. So as long as you know how much your beam moves along the y direction, okay, so the twice the derivative of y with respect to the x square will be equal to your curvature. So which means that if I want to find my curvature, I can use this equation. So if you modify the equation that I just showed you before, so ei over 1 over rho will be equal to mx. So 1 over rho is equal to d square y over dx square. So from there, this is the equation that you get. So which means that if you know what's your moment, okay, I can use this equation and I need to integrate it twice to get my y. So if you integrate once, okay, so this will be ei times dy over dx, and dy over dx is basically this angle of your beam, okay. So it will give you this tangent angle. So if you want to find the slope at any point in your beam, so I can use this equation. So this will be ei times the slope. And since we are dealing with small deformations, so tangent theta is equal to theta. So that's why I can use this equation. And so if you take the integral once, I need to integrate from 0 to x wherever I want to find my moment. And when you integrate, you will also get that one constant. Okay. And then if you want to find y, then I need to integrate one more time. So I need to do double integration of moment. And from here I will get c1x, and then I will get another constant. So which means that if you want to find your deflection, so you need to use this equation, and this is called the equation of elastic curve. So it will give me at any x what's my deformation amount. Okay, and then the question is, I see that when I integrate, I get these constants. Okay, how do I find them? So in order to find them, what I need to look at is I need to look at the boundary conditions. Okay, and for example, if you have a beam like this, okay, so this is simply supported beam. Since A and B are fixed, so since I have pins here, they cannot move along the vertical axis. So which means that YA and YB are equal to 0. So all I need to do is plug these numbers. So this is, for example, x is equal to 0, and this is x is equal to L. And then just solve this, and instead of y, it will be equal to 0. Okay? And same thing here. Since these are pins, I know that at these points, my deflection is equal to 0. If you have a fixed support, what you know is at point A, your deflection is 0, plus your slope is also 0. Okay. So this is something you need to kind of remember if you have a fixed support. So not only the deflection is 0, but your slope is also equal to 0. So depending on the problem, so you can determine what kind of boundary conditions you have, and you just plug this in this elastic curve equation, and you can get the constants you have. Okay, but just keep in mind that these are for kind of some simple cases. So you might also encounter the cases where you have more constants that you can get, and it means that for example, if the beam is kind of longer, okay, so then which means that when you get your elastic equation, you might need to use two of them. So you can get additional constants, but each of them you just need to look at the question and try to figure out what you can tell us about the deflection or the slope. So another thing is, so previously we learned that dm over dx is equal to vx. So if you take the derivative of m moment with respect to x, you will get the shear. Okay, and you know that if you take the derivative of shear, you will get the distributed load. So these are the things that we got before. So which means that I can also use this equation. Okay, and so if I take this equation and if I plug it, that's what we find before. So m was equal to ei times d square y over dx square. So it means that if you take the derivative twice, then I can get this equation. Okay, so this one is kind of sometimes useful. So if you have questions where you have distributed loads, or for example, if you want to use your singular functions, I can write my v as a singular function, and then if you want to get dy, so all I need to do is I need to take the integral 4 times. Okay, and in most general form, if you want to find dy, you just need to integrate it 4 times, and from there you can get what's your yx. Okay, and if you do that, then you will get, for example, in this case, you will get 4 constants. Okay, and how do I find those constants? For example, in this case, what I know is at a and b, my my ya and yb are equal to 0. Also, since when you take the derivative twice, basically you get m, okay? And I know that at point A and B, my moments are equal to 0. So I can also use this additional information, okay? And if you look at this condition on the cantilever beam, at A, I know that my A is equal to 0 and my slope is equal to 0. And if you look at point B, what you can say is, okay, so I don't have any moment, plus I don't have any shear force. So I can also use that one there, okay? So this time, in addition to my deflection or slope, I can also use, if I know what's my moment or if I know what's my shear force, to get this constants, okay? So I need to determine them from the boundary conditions. So what we will do is we will solve some more examples and we will try to understand how we can find our elastic curve for the questions that are given. So this is the first example. So I have this beam, or hanging beam, and I apply a P at point C. So the beam, the cross-sectional properties are given, so I can find my I. The modulus is given, so P is given as 50 kips, length, and A, and everything is given. So what I want to do is I want to derive the equation for elastic curve, and I want to determine the maximum deflection. Okay, and I want to find where it happens and also what is the value of that maximum deflection. Okay, so what I need to do is I will try to write my moment, because if I can find my moment, I can integrate it twice and I can get the equation for the elastic curve. Okay. All right. So when we start on this, so what I will do is I will just cut my beam. Okay. So the first thing is I have two reaction forces, so I need to determine it. And then what I will do is I will just cut it and I will try to find my moments. Okay. So first of all, I'm looking from A to B. So my analysis will be only between A and B. And so from your statics knowledge, you can find the reactions. You will find that this reaction is going downward. It will be PA over L. And this one, it will go up and it will be given by this value. So for this, if you cut it somewhere between A and B, okay. So since I know my reaction force, I know the distance, which I cut it at X, okay. So you can get that your moment will be given by this equation, okay. So this is what you need to do. So you need to be able to find your moment between A and B, okay. So, and again, this is only valid between A and B when X is equal to X is between 0 and L. So after I get this equation, now I can get the equation for my elastic curve. So I know that my moment is equal to EI times d square y over dx square, which is what I find by here. So what I need to do next is I need to take the integral. So this is the equation that I will start. So if you take the integral once, you'll get this equation. Okay, so I will get x squared over 2, and then I will get a constant. And if you take another integral, then it will be ei over y, and I will get these two constants. Okay, and next I need to determine these two constants. And from the question, what I know is since A and B, so A is pin and B is a roller, so there is no deflection along the y-axis. So which means that my y at x is equal to 0 and y at x is equal to L, they should be equal to 0. Okay, so from this equation, what I will use is I can use when x is equal to 0, y is equal to 0. So if you put it there, so this term is gone, this term is gone, only C2 is left. So C2 is equal to 0. And then I can also use the second one. When x is equal to L, y should be equal to 0. And from that, you can get your C1. And after you get your C1, all you need to do is just plug it back. And from there, I can get my equations for both EI dy over dx and EI y. Okay. All right. And from there, you can get what's your y given by this equation. So which means that between 0 and L, at any point, I can determine what's my deflection. Okay. So when you put x is equal to 0, for example, you will get 0. When you put x is equal to L, again, you should get 0. Okay. So after this, so next is I want to determine where my deflection is maximum. So how do you find the maximum of a function, maximum or minimum? So the best thing is take the derivative of this with respect to x, set it equal to 0, and you will get maximum or minimum points. So this is what we will do, and you will set dy over dx is equal to 0. And if you look closer, actually this is where you can also get that equation. So when you take the derivative once of your moment, actually you will get dy over dx. So you can also use this one, and this is a kind of given. So from this equation, after you determine your c1, you can determine the slope. Okay, so what we are looking at is we are looking at a place where our slope is 0, so which is this, it will correspond to this point E. Okay, and if you do that, so when you set it equal to 0, so and then you can find x. So when you get your x, this time it will be L over square root of 3, and you will end up with 0.557L. So which means that the coordinate of this point E, the x coordinate of point E, is given by this equation. And then all I need to do is I need to take this value and then just plug it to my equation for my elastic curve. So from there, for x is equal to L over square root of 3, this is the equation that you get. So your maximum deflection is given by this one. Okay, and since my moment is negative, I know that I should have concave down type of behavior from A to B, and so I know that actually I should go up, and you will get a positive value for your y. Okay. So if you kind of just do the math, this is the equation. This is what you will get. Okay, and then you can just plug the numbers, and if you plug the numbers, you will find that at point E, this is your maximum y, and it will be equal to 0.238 inch. Okay. So this is just an example. As long as you know your moment, I can use this. I can take the integral once, I can get the slope, and if you take the integral once more, then you can get the equation for your y, and then look at the boundary condition and apply it. But don't forget that this is only between A and B. I cannot use it between B and C, because the moment from B to C will be different than my moment from A to B. Okay, so you just need to be careful. All right, so what would you do if you want to find, for example, what's the deflection of point C? So what you should have done is do a kind of similar analysis, but this time what you need to do is you need to find your moment from B to C, and after you find it, your moment, so then you can relate your moment to your y, and then take the integrals, and then use the boundary condition, and etc. Okay, so again, this type of solutions, they highly depend on the question. So if you can, for example, if you can express your moment easily, so it's really I recommend it, just cut it, write your moment as a function of x, and then just the integrate it. But if you have complicated questions where you need to have so many sections, then it might not be very appropriate. So let's saw another example to find the deflection of a beam. So in this case, we have a beam from A to B, and we apply a load at point P, and we want to determine the deflection at point C. Okay, so in this case, when I analyze my beam, so what you will realize is your moment from A to C, the equation for your moment from A to C will be different than the moment equation from C to B. So I need to kind of have these two sections to analyze it. Alright, so first of all, let's find the reaction forces, and if you do that, this is B, from A to C is A, C to B is B, then I can get my reactions as given by this equation. Okay, and after that, if you want to find your moment from A to C, so whenever you cut it there, it will be equal to RA times X. Okay, so which will be equal to PB L over X, and whenever you cut it here, then you can get your moment equation given as this one. Okay, so this is important. Now when I look at this beam from 0 to A, I will have one moment equation, and from A to L, I will have another moment equation as a function of x. Okay, so this is why when I try to find my elastic curve, what I need to do is I need to divide it into two sections. So first of all, so the elastic equation from 0 to A for x between 0 and A, I will use this formula. And if x is between A and L, I need to use this formula. And then next is I will just integrate it. So I integrate once to get the slope, for the x is between 0 and a, and then you can integrate one more and you can get the your elastic curve. And you can also do the same thing for the second part between c and b. So you just integrate once and then you integrate it twice. So which means that here I get 4 equations. So which means that I have c1, c2, c3 and c4. So I have 4 constants. How do I find them? I look at the boundary condition. Okay. So if I look at the boundary condition, what you get is at point A and B, okay, so there is no deflection. So I can say that at A and B, so I don't have any y deflection. So y should be equal to 0, at x is equal to 0, and x is equal to L. And then what else can I get? So you can use the moment, but if you already, the moment equations are given there, and if you put x is equal to 0, you get 0. And if you put x is equal to L, this one will be also equal to 0. So you cannot use the moment is 0 at the end. But what I can use is, so this is a beam, okay, which means that the deflection and the slope should be continuous at C. So it cannot just deflect some from A to C and then jump. So my deflection to the left side of C and to the right of C should be equal to same. Same thing for the slope. So slope cannot updraft the change. So which means that my slope to the left of C and to the right of C, they should be same. So from there, I get these 2 equations. When x is equal to A, which is at point C, the deflections should be same, and also the slopes. So the slope should be same, and the deflections should be same. Okay. So from here, if you plug the numbers, so I'm using these 2 equations, equations number 1 and 3, so they should be equal to each other. And same thing I also use for the deflections. I'm using equations 2 and 4, so they should also be same. So which means that now I have 4 equations, so I can use this one, equation 1 here, and I can use equation 4 there, and then I have these 2 additional equations. So I have 4 equations, and I have 4 unknowns. And if you solve it, you can get that C1 is equal to C3, which are equal to this value, and you will also get C2 is equal to C4, and they will be equal to 0. Okay, and after that, if you write it again, okay, so this is my equation for the, I'm looking at the left side, so from A to C, and I can use it. And what I want to do is I want to determine what is this value when x is equal to A. So I'm looking at my deflection at point C, okay, and C2 is equal to 0, and C1 is given there. So from that, I can get this equation, okay. So which means that at point C, my y will be given by this equation, okay. And the cross-section array is given, so all the information are given there. And if you just plug the number, you can find that your deflection is given by this value. Okay. And again, if you want, you can also use the second. So if you also, you can use this equation. Okay. And all you need to do is just plug the number. Again, instead of x, you will put x is equal to A. Okay. And C3 is equal to C1, and C4 is equal to 0. So this method, it works fine, but the problem is, now I need to divide into 2 sections, and I need to integrate them, and then I need to use all these boundary conditions. So it's a little bit cumbersome. Okay. So in order to avoid this, what we can do is we can use our singularity functions. And we covered this in chapter 5. So you can look there if you are not feeling comfortable with it. But the idea is same. So what I can do is if I can get a single function, if you have distributed forces, you can use that one. You can start from there. Or in this case, we will start with the shear force. All I want to get is, I want to get an equation for the moment, which will cover the whole beam length. Okay. So in this case, I don't have any distributed load. So what I will do is I will just directly write my shear force. So by using singularity functions, I can write my shear force as given here. Okay. So let's assume that we apply a P at L over 4, and these are the supports. Okay. So which means that this is going up at when x is equal to 0, and I apply a load when x is equal to L over 4. So that's why I use this this expression, because this expression will be equal to 0 when x is less than L over 4. Okay, and then if you integrate it, and since I don't apply any moment, I can just write my moment by this equation. So don't forget that if you apply a moment, if there was a moment, this equation will be a little bit different. But if you don't have any applied couple, you just take the integral of this with respect to x, and this is the equation that I get. Okay, so this equation is valid for everywhere. So it's valid from A to D plus D to B. So it's valid from A to B. Okay, and then I can relate this to my elastic curve equation. So I know that this is valid. So from there, I can write this EI over D square Y over dx square is my mx. Okay, and then all I need to do is I need to integrate it once, so I can get my slope. And then if you integrate one more time, you get your deflection. Okay, and in this case, this deflection equation is valid from A to B. So I don't have four constants. So I just need to find these two constants. Okay, so if I write it back, so I just get these two constants, and I just look at the boundary conditions to determine it. All I need is I need two boundary conditions, and I can use at A and B, so there is no deflection. So I can just use this equation, and when x is equal to 0, my y should be equal to 0. When my x is equal to L, again my y should be equal to 0. Okay, so if you look at the first one, so when x is equal to 0, your y should be equal to 0, so you can plug it there. And this term is actually, it will be 0 because I'm using x is less than L over 4. Okay, and then from that you will get C2 is equal to 0. And then if you want to look when x is equal to L, just plug L instead of x, and this time I will just I will replace the brackets. They can just get out there, and I can just find my C1 is equal to this value. Okay, so the nice thing about this is, so I don't need to deal with four constants. Okay, I don't need to look at the continuity. So in the previous case, what I should have done is I should have found the moment from A to D and the moment from D to B, integrated twice, and then I need to use the continuity at D. So my deflection on the left and right side of D should be equal to same, and also my slope on the left and right side of D should be equal to same. So I can avoid it. All I can get is I can use simple equation for moment. So as long as you get this equation, all you need to do is just integrate it and get the elastic equation. If you have distributed forces, then you need to start from distributed forces. If you have any shear forces, you can start from this step. But our aim is to get an expression for moment for the whole beam, and then just integrate it twice and get one equation for the slope and one equation for the deflection. Okay. So if you do that, so it's kind of it will help us to skip some steps and easily be able to determine what is my deflection. Okay. So again, which method you choose is up to you. So you can either use singular functions, or you can divide into sections and just use the boundary conditions to find those constants. So you need to pick whatever you feel is you feel most comfortable with. So let's have another example, and this time let's have a distributed load. Okay, and what we want to do is, so we have this beam. So I want to get the equation of the elastic curve, the deflection at point B, and the deflection at point C. Okay, so first thing we need to do is, so when in this kind of questions, we need to be able to write the equation for this W. Okay, and also I will draw the free body diagram. So first we draw our free body diagram. Okay, so since this is fixed support, I will have a vertical force plus I will have a moment, and by using our static knowledge, you can write you can find your RA. Okay, and then you can find your MA. Okay, so these are the reaction force and the moment. Okay, and then what I want to use is I want to use my singularity function, and I want to write an expression for my W. Okay, so how do we write it? So when I look at this, so I don't have a W from A to B, but at point B, okay, when x is equal to L over 2, then I have my distributed load. So I can write my W by this equation. Okay, so when x is equal to L over 2, I will start getting this linear distributed load. Okay, and then you can find the slope. Okay, so when x is equal to L over 2, it will be equal to 0, and when x is equal to L, you can figure out that it will be equal to W naught. Okay, and then after this, what I can do is I can write my V, okay, and don't forget that this is my equation, okay. So when I write this equation, okay, so all I did is I just take the integral of it, okay. I need to take the integral of it, okay, and then I can write my V, but don't forget that I also have RA, okay. And so when you want to find your V, so I just need to integrate it by W, okay. And when you integrate your W, so I will just integrate this term, okay. But plus, since I have RA, I also need to add that one, okay. So since RA is 1/4 divided by double knot L, so I just put it there because it's applied at x is equal to 0, and I just add the integration of this term here, okay. And for the moment, so since now dm over dx is equal to V, so what I need to do is I just need to integrate this term, but plus I also apply this MA. So this is why when you find your M, it will be equal to my moment, okay. So it's applied clockwise, so you just add it there, okay. Plus I just need to add the integration of this term. So when you integrate, you will get x, and this is x squared over 2, so x cubed over 3, so this is why you will get the 1/3 there. Okay. So after I get this, so I don't need to worry anymore. All you do is after this, you just take integration of this term. So if you integrate once, you will get a constant, and just integration of this. What I want to do is after I get the equation for the slope, I can start using my boundary condition. Since this is fixed support, I know that my slope at x is equal to 0 should be 0. So I can use my first boundary condition. So when x is equal to 0, the slope should be equal to 0. So if you put it there, so you will see that all these terms, they are equal to 0. So from that, C1 is equal to 0. So I determine that C1 is equal to 0. So if you take this one and if you integrate one more, then I can get my equation for the deflection. So, and here C1 is equal to 0. I don't need to integrate it. So you just integrate all these terms and you will get this one. Okay. And after this, you can use another boundary condition. And since again this is fixed, I know that when x is equal to 0, my y is equal to 0. So from there, you will also determine that this C2 is equal to 0. Okay. So which means that for this question, so when you look at your elastic curve, this is the equation that you get. So you don't need to divide this into two sections. So this equation is valid from A to C everywhere. Okay. But don't forget that this one, it will be equal to 0 between A and B. Okay. And then if you write your slope, then this is the equation for your slope. And this is also valid from A to C. Okay. And in the question, it was asking about the deflection at point B. So which means that I will use this equation. And all I need to do is I need to put x is equal to L over 2. So if you take this equation and if you put x is equal to L over 2, this is what you will get. Okay. So which means that my deflection at point B is given by this equation. Okay. And since it's minus, it will go downward. Okay. And similarly, I can also find my deflection at point C. So this time, all I need to do is, again, I will use the same equation, but this time I will say x is equal to L. Okay. So here, if you put x is equal to L, this is what you will get. Okay. And again, it's going downward, and it's given by this value. Okay. So this singularity functions approach is really useful if you need to look at a beam and if you need to find the deflections or slopes at different points. Okay. If also otherwise, so if you just try to look from A to B, you cannot just get one moment and try to solve all the unknowns. Sometimes we get lucky and we can find all the unknowns, but sometimes what we need to do is we need to divide into a couple of sections, and then we need to use the continuity. Like at point B, the deflection and the slope should be same, both on the left and the right side of B. So it kind of makes our life easier if we use our singularity functions. So another topic in this chapter is determining the reactions or the unknowns from the statically indeterminate beams. So what we did before in chapter 2 is we solved some questions where we cannot directly get the normal forces of the problems. And what we did is we look at the deformations and from looking at the deformations we can get additional equations where we can find the unknown reaction forces and etc. And then in torsion we also did the same thing. We have statically indeterminate members there, and by just looking the angle of twist we determine what are the unknowns, but we didn't do it for the beams. And so in this chapter we will also deal with this with statically indeterminate beams. Okay, so as an example, if you look at this beam where you apply a distributed load W, A is a fixed support and B is a roller. So what you will see here is when you put all your reaction forces and moments, so at A I have horizontal, I have vertical and a moment. At point B I only have a vertical support. So when I look at this I have 4 unknowns, and from equilibrium I can get only 3 equations. So which means that I have 3 equations but I have 4 unknowns, so I cannot solve it. So what can I do is, so similar to what we did before, is I can get additional information if I look at the deflection. And if you find your if you write your deflection equation, this is what you will get. So when you write this I will get 2 additional unknowns. But if I look at the boundary conditions, what I know is at A the slope is 0 and the deflection is 0, and at point B deflection is 0. So I get 3 more boundary conditions, but from this equation I only get 2 unknowns. So the total is I have 3 equations here, and I have 3 equations from equilibrium, so I have 6 equations, and I have 4 unknowns here, and I have C1 and C2, so I have 6 unknowns. So from there it means that I can solve this question and I can find all the unknowns. Okay, so this is very analogous to what we did. So when we cannot determine the reaction forces or moments, if we have more unknowns than what we can use in equilibrium, then we need to look at the deflections, and from the deflections we will get some additional information, and we will use that information to find the unknowns. Okay, so we'll just solve examples and determine the forces that we cannot just determine by using our static knowledge. Okay, so this is a similar question. So again I have a beam. At B I have fixed support, at A I have roller, and this time I apply a linearly changing distributed load. Okay, and what we want to do is we want to determine the reaction at A, and we want to derive the equation for the elastic curve, and we also want to determine the slope at A. Okay, so in order to do this, what I need to do is first I need to determine the differential equation for elastic curve, and then integrate twice, and then apply boundary conditions and try to solve the unknowns, and then I can determine the slope. Okay, so in this question, so it's clear that I have only one section, so I'm not going to use the singularity function, but if you want you can also start with that one. But for this one, since this is just one section, I will just cut it at the x location, and I will just try to write my moment. Okay. So if I cut it when x is equal to x, so in an arbitrary x, so what I will get is I will get a shear force and I will get a moment. Okay, and then so you can find the equation of this line. So it will be equal to W naught x over L. So when x is equal to 0, your W naught is equal to 0. When your x is equal to L, it will be equal to W naught. So this is the equation of this line. Okay, and then so if you write your moment at point D, so what I have is, if you take a moment there, I have RA times x. Okay, and then I have the 1 over 2, so it's the area under this triangle, times this length, W naught x over L, times x. Okay, so it gives me this area, and I need to multiply with the distance, which is x over 3. Okay, and then I have this counterclockwise m, so I just put it there. Okay, and here I'm assuming that if it goes clockwise it's positive, so this is positive, so this is negative, and m is negative, and from there you can get your m as this equation. Okay, so this is valid between A and B, so it's valid along the whole beam section, and So this is my moment. If I know my moment, then I can get my y. So I can write this equation. So EID is I squared dx squared is equal to m, and I find my m, so I just plug it there. Okay. So again, this question, it was simple enough. I can directly get my m. So this is why I didn't do the other things. Okay. All right. And then what I can do is, after I write this, so I just need to take the integration. Okay. And if you integrate once, you will get the slope. If you integrate one more time, you will get the deflection. Okay. And when you do that, you will get this unknowns. Okay. So when I look at this, I don't know what's RA, I don't know what's C1, and I also don't know what's C2. So I have 3 unknowns. And then if I look at the boundary condition, so here this is roller, so I know that y equal to 0. And here this is a fixed support, so I know that y is equal to 0, and the slope also is equal to 0. And from there, it means that I have 3 boundary conditions. So when x is equal to 0, y is equal to 0, I just use this equation, and you can find that C2 is equal to 0. And I can use x is equal to L, which theta is equal to 0. So I can use this one. Okay. And then at x is equal to L, y is equal to 0. So I have this equation. Okay. And C2 is already 0. So it means that I have 2 equations, 2 unknowns. And then from there, you can solve for RA. Okay. And when you solve it, this is the equation that you will get for RA. Okay. And if I go back to my question, so I couldn't find that one normally because so I have RA here, I have RB here, plus I have a moment. Okay. And you can also consider the horizontal force. So again, I have 4 forces, but I can only 4 unknowns. I get only 3 equations. So I couldn't determine what's my RA. But now, by looking at the deflection curve, I figure out that my RA is equal to 1 over 10 W naught L. And after I get my RA, then I can go back and I can write my equation. So this is the equation for deflection. So I plug my RA, okay? And from there, you can get the equation for deflection. So at any x, I can determine what's your deflection. And then, so if you go back and then you can also get your equation for slope. So slope is equal to dy over dx. Okay. And then from there, this is the equation for your slope. Okay. And if you want to find the slope at a, then you need to plug at x is equal to 0. So from that, you can get the slope at a. Okay. But by using this equation, you can get the slope anywhere. Okay. And when you put x is equal to L, you will see that this is equal to 0 because it's a fixed support. Okay. And also, when you find your M, so since your M was positive, so since this was clockwise, it was positive, so which means that you have concave up deformation. And if you look at the deflection, this is what you will see. Okay, so you will have this deformation. Okay. So this is one example where I couldn't find my RA, but now by using the looking at the deflections, I can find my support at A, and after you find your support at A, I can find my deflection and the slope anywhere I want. Alright, so again, this one, the question from A to B, the moment was same. So I can express it, not same, but I can express it with one equation. So I didn't need to divide into sections, okay? But you might get some other questions where your moment will not be same everywhere, okay? So if you look at this question, so we have this beam, A to C, and we have distributed load applied from A to B, constant distributed load, and we want to determine the reaction at point C and the deflection at point B. So if you look at this question, so this is very similar, but when you draw your free body diagram, what you will realize is, so it will look something like this. So you apply a load here, and you have 2 vertical loads at A and C, plus you have a moment at A. So when you look at this, you have 3 unknowns, and you have only 2 equations, because on the x there is nothing. Okay, So which means that if from statics, when you write your equation, so this is the first one I can write, the total forces on y equal to 0. And then you can also get a moment, and then you will get another equation, okay? So from here, I can get my RA in terms of RC, and I can get MA in terms of RC, but I cannot find them. So I have two unknowns. I have three unknowns, but I have two equations. So I need one more equation. So this is why this is statically indeterminate. Okay? And then what I need to do is, so when I look at this, so I have two sections. So from here, from A to B, okay, I have distributed load, but from B to C I don't have anything. So normally if you want to write your moment, your moment equation from A to B will be different than your moment equation from B to C. So you have two options. Either you can separate into two, and then you can write a moment from A to B, and then from there you can get your deflection equation. And you can also do the same thing from B to C, and then you can use the boundary conditions and also the continuity equation at point B. But there will be a lot of unknowns, and it's going to be too complicated. So what I can do is, instead of dividing into two sections, I can use singularity functions. So first thing I need to do is I need to be able to write my W, okay? And in this case, so if you go back and if you look at here, so my W starts from 0, and since what I need to do is I need to assume that it goes all the way to C, and then I will apply another W from B to C on the opposite direction to kind of cancel it. So this is why when you write your Wx, it will be like this. So I have constant W. I'm assuming that I apply from A to C, and then I'm assuming that from B to C I kind of apply in the opposite direction, so they will cancel each other, and there will be no distributed load from B to C. Okay, so this is how I can express my my distributed load in singular function. And then what I need to do is I need to write my V. Okay, so dV over dx is equal to minus W. So I just write the minus of this equation, and then I need to get my V. Okay, my shear force. So in order to get my shear force, I need to integrate this with respect to x. Plus, I also have an RA here, so I also need to include that one. So when you write your V, so my V is equal to RA, so since you apply RA here, and then minus 14 times x, so this one, it's because of the integration, and if you just integrate it, it becomes 14x minus 5 to the power of 1. Okay. And this is equal to dm over dx, so if you want to find m, you need to integrate this one, okay? And so when you integrate it, don't forget that you also have a applied couple here, so you also need to add that one. So which means that when you write it, so I will have MA, okay, because here it's clockwise, so I just put MA, plus integration of this one, RA times x, minus 14 times x squared over 2, plus 14 times x minus 5 square of 2 minus divided by 2, so you will get this one for your m. And after you get your moment, I can say that it's equal to EI times d square y over dx square. Okay. So our aim by using singularity function is getting the expression for moment. Okay. So this is why we started from distributed load. We integrate it once, and since I have some other point loads, you just add them. Okay. And then if you want to get your moment from your shear force equation, you integrate it with respect to x. And then since I also have some moments, you also add them there. Alright, so since we covered this, I'm not going to be going into details, but this is our aim. Our aim is to be able to write our moment in singularity functions. And after you get this, you just need to take the integration. So you integrate once, you get the slope, and here you also get a constant. And then you integrate one more, and then you get another constant, and this is the equation for our deflection. Okay. Alright. So these are the two equations we got. So this is the equation for slope, and this is the equation for the deflection. Next is I will apply my boundary condition. So when you apply the boundary conditions, I always like to start with the slope, because in slope I only have one constant. So if you have any boundary conditions related to slope, it might be better to use it. Okay. So for example, here we know that when x is equal to 0, our slope is 0. So if you plug it there, you will find that your C1 is equal to 0. So our first constant will be equal to 0. And then I can use the second boundary condition. So I know that at this point my y is equal to 0. So when x is equal to 0, my y is equal to 0. So now I will use this equation. So just put x is equal to 0 and you end up with C2 is equal to 0. Okay. So I got my C1, C2. So then I still need one more equation that I need to relate this MA to RA. Okay. So for that I will look at point C, and at point C I know that my y is equal to 0. So when x is equal to 8, y should be equal to 0. So if you plug this once, so you can get this equation. And previously we learned that I can write MA in terms of RC, and I can also write RA in terms of RC. And so if you combine all those equations, this is what you will get, and from there you can get your RC. Okay, so you can get the support force at C, and after you get your support force at C, then you can also get what's your support at A, and you can also get what's your moment at A. Okay? So from there I can get all the unknowns that I need. Okay? All right. So with this, I find what's my moment at A, and I can find what's my force at A. Okay. And after I get this, so rest is just applying equation. So it was also asking what is the deflection at point B. So this is our deflection equation. So we find our MA, and C1 and C2 are equal to 0. We also figure out what's our RA. So all I need to do is at x is equal to 5, I need to find my y. So you just plug the numbers there, and you get that your YB is given by this equation. So it should be downward by 4.18 millimeters. Okay. So this is the power of using singularity functions. So if you can get this moment expression throughout the beam, then rest is just taking the integrals and just using the boundary conditions. But we need to be careful. So when we are getting this moment, so if you have distributed load, start from the distributed load equation and take the integral, find V, and if you have any force applied, so you just need to add that one. And then after you find your shear force equation, you can take another moment, another derivative, and you can get an expression for moment. But don't forget to add if you have any applied couples there. And after that, just take two derivatives and look at the boundary conditions and plug them there. Okay. So which method you will use is up to you. So either you can use singularity functions, or if you don't feel comfortable, you can divide this into sections, and for each sections you can get the moment. After you find the moment, you can just integrate it, get the slope. You can integrate one more time, you can get the deflection, and then you can use the boundary conditions, plus you can also use the continuity equation. Okay. Condition. So with this, so this was the first part of this chapter, and we will continue the second part where we will kind of use tables to do what we did in this part.